Okay. This afternoon, we want to talk about something called conservation of linear momentum. We especially want to talk about conservation of linear momentum in the case of where things are colliding, when objects collide. So, when there's collisions or when there's explosions, there is always what is referred to as conservation of linear momentum. The linear momentum before a collision or the linear momentum after just before things collide and just after things collide, the total linear momentum before and after the collision appears to be the same. So if you have what we know what momentum is the mass of an object multiplied by the velocity of that particular object. So if you have got a bunch of things about to collide, so you work out what the total momentum is just before they collide and what the total momentum, linear momentum, is after they collide. Then the principle of conservation of linear momentum basically says that the momentum is conserved. So we want to see what this is, the principle of conservation of linear momentum, and we want to apply this principle of conservation of linear momentum to a bunch of simple problems so that we can see how this conservation of linear momentum is applied. Then we are also interested in collisions, and there are two types of collisions we're interested in. We're interested in elastic collisions and plastic collisions. So these collisions, whether it's elastic or plastic, has to do with the kinetic energy of the objects which are colliding. What is the sum, or what is the total kinetic energy of the objects before the collision, and what is the total kinetic energy after the collision. So if the kinetic energy just before the collision of the objects involved in the collisions is the same as the total kinetic energy just after the collision, then we say that such a collision is an elastic collision. Usually, that's in very few cases when you have got elastic collisions. Most of the collisions which objects undergo are in elastic collisions where the kinetic energy of the objects before the collision and after the collisions are not the same. So when it comes to kinetic energy, there are cases when kinetic energy is the same before or after. So if kinetic energy is the same before or after, then we say that it's conserved. In the case of linear momentum, the linear momentum before a collision, the total linear momentum before a collision, and the total linear momentum after a collision is always conserved. So that bit we're going to look at, and we're going to use that fact. Okay. Yeah. So let's start with linear momentum and its conservation. So the first thing we need to be aware of is that linear momentum is a vector. So we are dealing with vectors. So when you're talking about linear momentum is a vector. The direction of the linear momentum is the same as the direction of the velocity. So as you try to apply this conservation of linear momentum thing, it is very important that you choose a direction. Which direction is going to be positive? And if you have got a certain positive direction, then the opposite of that is going to be a negative direction. So that's the first thing. You need to be aware that linear momentum is a vector. Then the principle of conservation of linear momentum says that the total linear momentum is constant. It's conserved. The total linear momentum is always the same before and after a collision or an explosion. The total linear momentum before a collision or an explosion, the total linear momentum after a collision or after the explosion has to be the same as the total linear momentum before. It's always conserved. So this is what is referred to as the principle of conservation of momentum. And like I've said, you have to be aware of direction. You need to be aware that momentum is a vector, and when you're talking about vectors, it means that direction is important in this case. So that bit has to be taken into account. The principle of conservation of linear momentum states that linear momentum with momenta of bodies before they collide or explode is the sum of all the linear momentas will be the same afterwards. So basically, for you to work out the total linear momentum in this case, you need to work out what is the momentum of each and every body before this event happens, a collision or an explosion. What is the momentum? Then after you work out these momentums, you add them so that you can find the sum of this linear momentum. So the sum of the linear momenta before the collision happens and just after the collision has to be the same. Now here, there is a requirement for this to work. The requirement is that no external force acts on the objects in question. This is the requirement. This principle depends on the condition that no external force acts on the objects in question. What does an external force do? An external force is going to change the velocity of objects. So there should be no resultant force acting on these particular objects. It's either these objects involved in the collision, either they have they should have the same velocity. How can an object have the same velocity? Either the object is at rest or the object is moving at constant velocity. So you cannot apply the conservation of linear momentum when the velocity of the objects which are involved in, whether it's a collision, which are about to collide, or exploding, when their velocity is changing. If there is acceleration, then you can't apply this conservation of linear momentum. You can only do this, apply the principle of conservation of linear momentum, when the objects involved in this situation, whether it's a collision or an explosion, when their velocity is the same. They have to be moving at constant velocity. So the velocity has to be the same, the object has to be moving with the same velocity throughout, or the object has to be at rest. Are we clear with these things we're talking about? There should be no external force acting on any of the objects. If an external force is present, that external force will change the velocity of that particular object. You end up having acceleration. So the requirement for you to use this principle of conservation of linear momentum is that these objects which are involved in this collision should not accelerate. It's either the object is moving with constant velocity or the object is at rest. So basically, those are the situations which we're going to consider. Things colliding or things exploding, then before the collision, these things are moving with the same velocities, then they collide, or after the collision or explosion, they move out with the same velocity, like that. So let us look at how we would apply conservation of linear momentum during a collision. So in this case, we have a scenario which you have to look at. So during a collision of two bodies of masses m1 and m2, so you've got an object of mass m1 and m2, the sum of the linear momenta of the bodies in the x and y directions before and after they collide is always the same. So we are told that when you have got objects of mass m1 and m2, when you add the linear momentum of these objects along the x direction and along the y direction before and after they collide, the linear momentum should be the same. Therefore, if a body with mass m1 traveling at speed u1 collides with a body, so here, therefore, if a body with mass m1 traveling at speed u1 collides with a body with mass m2 with velocity u2, the two masses will proceed with momentum with velocities v1, this is after the collision, and v2 after the collision. So you have got bodies, mass, or the first object with mass m1, before they collide, it collided with the other object at velocity u1. Then the second object, mass m2, the velocity of the object was u2. Then after they collide, of course, the mass, we are assuming that after they collide, the masses of these objects still remain the same, but their velocities have to change. So the first object with mass m1 ends up having velocity v1, and the second object with mass m2 ends up having velocity v2. So in this case, the total linear momentum before and after the collision has to be the same. So here we say total linear momentum before collision and total linear momentum after collision has to be the same. That is a requirement. Okay. This can be extended because we are interested in what the velocity of this particular object is along the x-axis and along the y-axis. So this requirement that the total linear momentum before collision and the total linear momentum after collision should be the same, this requirement can be extended along the x direction. You can say the total linear momentum along the x direction before collision and after collision along the x direction has to be the same. Also, you can extend this to say the total linear momentum before collision along the y direction and after collision along the y direction has to be the same. So these velocities we have here, u1 and u2, these are the velocities of these masses m1 and m2. So those are the velocities of the objects m1 and m2. So in this case, we need to find how much u1 and u2 is along the x-axis. You also need to know how much u1 and u2 is along the y-axis. This velocity u1 along the x-axis is going to be u1x, which is the x component of the velocity along the x-axis. Then this velocity u2 along the x-axis is going to be u2x, which is the x component of the velocity along the x-axis. You also be interested in finding out what the velocity of these masses are along the y-axis. So in this case, this one, u1 along the y-axis is going to be u1y. Then this one here along the y-axis is going to be u2y. So it's very important that you find out how much the velocity of the object is along the x-axis and along the y-axis. For each velocity you're given, you need to find the x component of the velocity, you need to find the y component of the velocity. Similarly, after the collision, here with this velocity v1, you need to find the x component of this v1, how much is v1 along the x direction and how much is v1 along the y direction. So you're talking about v1x, then also and v1y. So v1x is going to be the velocity of the mass 1 along the x direction, and v1y is going to be the velocity of mass 1 along the y direction. Similarly here, v2 is going to be, in this case, you need to find how much this velocity is along the x direction, so that's going to be v2x. You also need to find how much this velocity is going to be along the y direction, that is going to be v2y. So what you're trying to say here is that this is the most general form of the principle of conservation of linear momentum. However, for this to be true, we need to enforce this requirement along the x direction and along the y direction. So in that case, like I've said, for the masses along the x direction, the velocity we're looking for is v1x. We need to find how much v2x is. Then we also need to find u1x here, u1x, which is the velocity of the mass 1 along the x direction before the collision, u2x, the velocity of mass 2 along the x direction before collision. Then you need to find v1x, the velocity of mass 1 after collision along the x direction, then v2x, which is the velocity of mass 2 after collision along the x direction. Then we are also interested in finding the components along the y direction, so you need to find this one, v1y, which is the velocity of the first mass before collision along the y direction. Then you need to find this guy here, v2y, which is the velocity of mass 2 along the y direction before collision. Then you also need to find this one, v1y, which is the velocity of mass 1 after the collision along the y direction, and you need to find this one, v2y, which is the velocity of mass 2 after collision along the y direction. With these components found, so basically what you're saying is, For each velocity, whether it's a velocity before the collision for a particular object, you need to find its x components and y components. For each velocity of the object before the collision and after the collision, you need to find its x components and y components. Once you do that, then you can apply this principle of conservation of linear momentum before and after collision along the x direction. So in this case, we're going to talk about the first mass, which is m1. Then we multiply it by the velocity. We multiply it with the velocity, with its velocity before collision along the x direction, which is u1x, plus mass 2. Then we multiply this mass 2 with the velocity of this mass before collision along the x direction, which is u2x. This bit here, this gives us the sum of this gives us the total linear momentum before collision along the x direction. This has to be equals to the total linear momentum after collision along the x direction. And how do we get that? It is the mass 1, the velocity, the mass 1 multiplied by the velocity of this object after collision along the x direction, which is v1x, plus mass 2 multiplied by the velocity of this object after collision along the x direction, which is v2x. So here, so this is how we express our conservation of linear momentum along the x direction. We can do the same thing, similar thing, along the y direction. So along the y direction, we can also impose this principle of conservation of linear momentum to say, even along the y direction, the total linear momentum before collision and after collision needs to be the same. So in this case, we have m1, which is the mass of the object, multiplied by the velocity of the object before collision along the y direction, which is the y component of the velocity u1, plus mass 2 multiplied by the velocity of the object before collision along the y direction, which is u2y. This bit gives us the total linear momentum before collision along the y direction. This has to be equal to the total linear momentum after collision along the y direction. So in this case, you end up having m1 multiplied by v1y plus m2 multiplied by v2y. So these two equations are what we use. So these two equations are what we use to impose the fact that conservation of linear momentum always occurs when objects collide. Are we clear? Are we clear on these two equations? We use these equations to impose the fact that the total linear momentum before and after collision has to be the same. It is also very important that you choose direction, so that if a velocity is in a particular direction you've chosen to be positive, that velocity will be positive. If a velocity is pointing in a direction which is negative to what you've chosen, that is going to be a negative velocity. Okay. Another thing which sometimes we look at, so basically this always has to happen. So the principle of conservation of linear momentum is always upheld. Okay. You can also look at collision in terms of energy, where there is change in kinetic energy. Okay. In some cases, like I've mentioned earlier, the kinetic energy might be the same. The total kinetic energy before a collision and after the collision might be the same. The kinetic energy of these particular objects might be the same before or after the collision. In some other cases, the kinetic energy after the collision is not the same as the kinetic energy before the collision. So in this case, we have to look at things in terms of energy, and since these objects we are looking at which are colliding are moving, so they always have kinetic energy, and we are assuming that the objects are colliding or moving on a flat or horizontal surface. So if the objects are moving on a flat or horizontal surface, so in that case, we can have the kinetic energy Ke equals to half mv squared equals to p squared divided by 2m. So we know that kinetic energy is equals to half mv squared, which is equals to the momentum squared. So if you know what the momentum is, momentum squared divided by 2m. So things can be looked at in terms of kinetic energy. So the total kinetic energy, like I've said, the total kinetic energy of bodies before they collide, before the collision, and after the collision can be the same or it can be different. The collision which results in the preservation of kinetic energy before and after the collision, these are called perfectly elastic collisions. So if the kinetic energy, the total kinetic energy before things collide and the total kinetic energy after things collide is the same, before the collision and after the collision is the same, then we call such a collision a perfectly elastic collision. Usually, there is always loss in kinetic energy because there is friction or there is heat, there is sound, and also sometimes there might be change in potential energy. So if there is change in potential energy, then the collision is not going to be elastic. The kinetic energy after the collision and before the collision is not going to be the same. So if the kinetic energy is not the same, then in such a case, we call such collisions inelastic collisions. Even in an inelastic collision, the principle of conservation of linear momentum is still upheld. So conservation of linear momentum is still very much upheld even when you have collisions which are inelastic and elastic ones. So if you've got an elastic collision, we are saying that in an elastic collision, the kinetic energy before and the kinetic energy after should be the same. So since our mass m1 was moving with velocity u1 before they collided, so you can work out what the kinetic energy is. In this case, it's going to be half m1 multiplied by u1 squared plus half m2 multiplied by u2 squared, which is equals to half m1 v1 squared plus half m2 v2 squared. So this is a case where the kinetic energy, the total kinetic energy before these objects collide and the total kinetic energy before objects collide happens to be equal to the total kinetic energy after the objects have collided, and this is what we refer to as an elastic collision. So when it comes to collisions, there are two types. Where there is conservation of kinetic energy, so if the kinetic energy is conserved, then we say it's an elastic collision. If kinetic energy is not conserved, then we say it is an inelastic collision. Any questions before we start looking at examples? Because what comes after this is just example after example after example. Any questions? Okay, so if there are no questions, then we'll look at example number 1. An 8-gram bullet fired horizontally into a 9 kg cube of wood, which is at rest. I think it's supposed to read an 8-gram bullet is fired horizontally into a 9 kg cube of wood, which is at rest and sticks in it. The cube is forced to move and has a speed of 0.4 meters per second after impact. Find the initial velocity of the bullet. So in this case, we have a bullet which has been fired from the gun. And like we have said, when you're looking at these problems of collisions, the one thing you're supposed to a requirement here, one of the requirements is that there should be no external force acting on any of the objects in question. If there is no external force, then you assume that the velocity of these objects which are colliding is constant. So in this case, we assume that when the bullet is fired from the gun, it comes out of the gun with a certain velocity, which we do not know at the moment, and that's the velocity you are looking for. So the bullet has got a certain velocity which is fired with from the gun, and you are looking for this velocity of the bullet. This velocity before impact doesn't change, it's the same. Okay, because there is no external force acting on any object. So if there is no external force acting on any object, then it means that the velocity of this object is going to be the same. So this bullet, when it's fired from the gun, it has got a certain value of velocity which we are looking for. This bullet strikes, it hits into the wooden block, but before the bullet hits into the wooden block, we are told that the wooden cube has got a mass of 9 kgs and it is at rest. So the cube was at rest. The velocity of the cube was 0 meters per second since it was at rest. So we know the mass of the cube and we know the mass of the bullet. The bullet was moving with a velocity which is not 0. The cube was at rest, meaning that the cube had a velocity which is equal to 0. When the bullet hits into the cube, then gets stuck, the act of a bullet hitting the cube, that is a collision itself. And we are told that the bullet gets stuck in the wood. So when the bullet gets stuck in the wood moves, which means that the wood and the bullet move with the same velocity after it gets stuck, after impact. And that velocity is 0.4 meters per second. So we know the velocity of the bullet. We also know the velocity of the wood. After impact, it is 0.4 meters per second because the bullet gets stuck in the wood. So with this, we know we can apply the principle of conservation of linear momentum to say, since this whole thing is happening in a straight line, we can use this equation, this one here, along the x direction. So we know the whole thing is happening in a straight line. So we can use one of those equations there. And for us to use that equation, we need to know the mass of the bullet. So the mass of the bullet here, mb is 8 grams. But we do not do calculations in grams. We have to do calculations in kgs. So that 8 grams becomes 0.08 kgs. The mass of the bullet is the velocity of the bullet before it strikes the wood. That's what you're looking for. And we denote that as UB, initial velocity of the bullet. The wooden cube, we denote its mass as MW, W for wood, and the mass of the cube is 9 kgs. The velocity of the wooden cube, we denote that as UW. This is before the bullet hits the cube. Now, the cube was at rest, therefore its velocity is going to be equal to 0 meters per second. So with this, we know the mass of the bullet is 0.008 kgs. We know the velocity, the velocity of the bullet is just UB, but we do not know its value. That's what you're looking for. We know the mass of the wooden cube, that's 9 kgs. We know the velocity of the cube. Before it was struck by the bullet, it was at rest, so therefore the velocity is 0 meters per second. So with this information, we can work out the total linear momentum before the bullet struck the wood. So in this case, the total linear momentum is going to be the mass of the bullet multiplied by the velocity of the bullet, which is UB, plus the mass of the wood multiplied by the velocity of the wood. Now we know that the mass of the bullet is 0.008 kgs multiplied by the mass of the bullet, which is UB. This is what you're looking for here, plus the mass of the wood, which is 9 kgs multiplied by the velocity of the wood, which was 0 meters per second. So in this case, this 0 meters per second multiplied by 9 kgs is going to give you a 0. So in this case, this whole thing just becomes 0.008 kgs UB. So this is the total linear momentum before the bullet struck the wood. After the bullet struck the wood, we are told that the bullet got stuck in the wood. So the wood and the bullet moved together, and the velocity they were moving at after the impact was 0.04 meters per second. Just after the bullet struck the wood, this bullet and the wood, they moved together, and the velocity was 0.04 meters per second. Like that. So in this case, we can find out, we can find out the total mass since the bullet gets stuck in the wood. So the mass of the bullet plus the mass of the wood, which is what you have here, the mass of the bullet plus the mass of the wood. So this is going to be 0.08 kgs plus 9 kgs, which gives us this So this is the total mass of the whole thing, the whole arrangement, since the bullet gets stuck in the wood. And this bullet and wood combination moves, after impact, it moves with this velocity. So we can find out what the total linear momentum is after impact. So that's going to be the mass of the bullet plus the mass of the wood. You add them together, then you multiply by the velocity, and this velocity you have been given is 0.4 meters per second. So that's going to be 9.008 kgs multiplied by 0.4 meters per second, and this gives us this much linear momentum, 3.6032 kgs meters per second. So this is the total linear momentum after the bullet, just after the bullet hit the wood. Okay, so the principle of conservation of linear momentum requires that the total linear momentum just before impact and the total linear momentum just after impact should be the same. So the total linear momentum just before the bullet struck the wood, this is what you have here, 0.008 kgs UB. Then the total linear momentum just after the bullet hit the wood, this is what you have here, 3.6032 kgs meters per second. So these two quantities have to be equated. So when we equate them, as per the requirement that the total linear momentum before impact should be equal to the total linear momentum after impact, so we equate them, so you end up having this one, 0.008 kgs UB. So this is the total linear momentum just before impact. Then this side here, 3.6032 kgs meters per second. This is the total linear momentum just after impact. So with this expression, you can work out UB by dividing both sides by 0.008 kgs. So when you do that, you end up having UB, which is the velocity of the bullet, being equal to 3.6032 kgs meters per second divided by 0.08 meters per second, and you end up having a velocity V of 450 meters per second. So this UB, 450 meters per second, is the velocity with which the bullet was fired from the gun. And we assume that the velocity is the same. It doesn't reduce in velocity or it doesn't increase in velocity, because all the objects in question here do not experience a net force or a resultant force. Is that clear?
Yes, sir.
Okay. We move on to another example. Here, example number 2. Again, this is a collision problem. Now we are told there is an x direction. Okay, so it reads as follows. A 16-gram mass is moving in the positive x direction. So positive x direction. So assume imagine you've got an xy plane. Okay, so this mass with 16 grams is moving in the positive x direction at 0.3 meters per second, while a 4-gram mass is moving in the negative x direction at 0.5 meters per second. They collide head on and stick together. Find their velocity after collision. So here you have two objects, mass 1, what you're going to call the first object has got a mass of 16 grams. It is moving in the positive x direction, so the velocity of the object is plus 0.3 meters per second since it's moving in the positive x direction. Then there's another mass, this one, 4 grams, moving in the opposite direction, in the negative x direction, so the velocity of the object is going to be minus 0.5 meters per second. The reason why we are looking at direction, because velocity is a vector. So depending on where the velocity is pointing, you put a negative or you put a positive. Okay, so we let this 16-gram mass to be mass 1. So mass 1 is going to be 16 grams, and 16 grams in kgs is 0.016 kgs. The velocity of this mass 1 along the positive x direction, we are told it's 0.3 meters per second. This is the velocity before the collision. This is the velocity before the collision. So this 0.3 meters per second, it's along the positive x direction. So this velocity, we give it a positive sign. And since it's the velocity of the first mass, we call that u1. So it's going to be u1 equals to plus 0.3 meters per second. Then the second mass, this one, we're going to call this m2. So m2 is 4 grams, and in kgs, that is 0.004 kgs. This one is moving in the negative direction. Since it's moving in the negative direction, this velocity it has is going to be negative. We're going to give it a negative sign since it's moving in a direction which is opposite. And it is the velocity of the second mass, so we're going to call it u2. U for initial, the velocity, u is for the velocity of the object before they collide. U is velocity of the objects before they collide. V is for velocity of the object after the collision. So in this case, u2 is minus 0.5 meters per second. So with this information, we can work out the total linear momentum before the collision. So the total linear momentum before the collision is going to be mass 1 multiplied by the velocity of mass 1 before collision, which is u1, plus mass 2 multiplied by the velocity of mass 2 before collision, which is u2. Our mass 1 is this one, 0.016 kgs, multiplied by the velocity, which is plus 0.3 meters per second. Then this one here, positive 0.3 meters per second, then plus. We are doing a sum. We're looking for the total linear momentum of these objects before they collide. Then we come to the mass of the second object, which is 0.004 kgs, multiplied by the velocity of the object. This object is moving in an opposite direction, in the negative direction, so the velocity is negative here, minus 0.5 meters per second. When you work out this total linear momentum before the collision, what you end up with is this one here. You end up with 0.0028 kgs meters per second. So this is the total linear momentum before they collide. Now, we are told that after they collide head on and stick together. So if they collide and stick together, then they have the same velocity. That's the first thing you notice. They have the same velocity and they are working as one object. So in this case, the masses of these objects, since they stick together, they become one object. So we need to, the mass of the object after collision is no longer just one, because they have stuck together is now 2. So the total linear momentum just after collision is going to be the sum of the masses, which is m1 plus m2, multiplied by the velocity which the objects have after they have stuck together, and this velocity is what you're looking for. So the masses are, in this case, the masses are these ones here, 0.016 kgs plus 0.04 kgs multiplied by v, and this is going to give us 0.02 kgs multiplied by v. So this is the total linear momentum just after these objects have collided. Again, conservation of linear momentum. The total linear momentum before they collide, which is this one, and the total linear momentum after they collide, which is this one, they have to be the same. So we kept these momentums. So total linear momentum before collision and total linear momentum after collision, they have to be equated. So we end up having this one, which is 0.0028 kgs meters per second. This is the total linear momentum before collision, being equal to this one, which is 0.02 kgs v, which is the total linear momentum after the collision. So with this being equal, we're looking for v, so you can divide both sides by 0.02 kgs. So when you do that, you end up having v equals to 0.0028 0.0028 kgs meters per second divided by 0.02 kgs, and we end up having a velocity of v equals to 0.14 meters per second. So after they collide and stick together, the velocity of the objects immediately after collision is 0.14 meters per second. Are we clear?
Yes, clear.
Yeah. So today we stop here. We're going to continue on Thursday at 8 hours. The video recording of what you have done so far is going to be uploaded to YouTube so that you can have a look at it again. The notes are already available on Moodle, so you can download the notes and have a look at them ahead of time. Okay, unless there are any questions, we'll stop here. Any questions? Okay, so we stop here. See you on Thursday.